Hey guys, Miss Miklos here, and today's lecture is going to be pretty quick, which I'm sure you will be happy about. And the reason why it's going to be quick is because it is pretty self-explanatory. In fact, we learned all this stuff back in Algebra 2, so today we are specifically talking about properties of logarithms. And we're going to use this fabulous formula, the change of base formula, and the reason why it is amazing is because it allows us to put anything we want into our calculator. Up until now, there have only been two logarithms, two bases that we could put in our calculator. The first was our ln, and we know that that means log base e, and that was our natural logarithm, and our second one is log, which is our common log, which is log base 10. Using the change of base formula, what this is saying is log base a of x is the same as log base b of x over log base b of a. And quite honestly, I think that looks a little bit complicated. So I just want to break this down into two different ways that you can use this. So the first way, if we have log base a of x, you could go ahead and say log of x divided by log of a. What I always remember is that whatever's in the subscript stays in the denominator. So it's already down below, it stays down below. I also just want to stress to you guys the importance of using parentheses. If I do not close this parenthesis, then I'm actually taking the logarithm of x, whatever that value is, divided by the logarithm. Instead of just doing the log of x, closure, divided by the log of a. The second method, and I will demonstrate both for you guys, don't worry. If we have log base a of x, we could also say that that is like ln of x divided by ln of a. So the whole point of this fancy looking formula is saying that I can change the base into whatever I want as long as I'm consistent with the numerator and the denominator. Now the only two we're going to change it into is log and ln because those are the only two that we can do in our calculator. So for 1 and 2, we're going to go ahead and transition now into our calculator, and I'm going to demonstrate what this looks like. Okay, so now we're going to go ahead and look at number 1, which is log base 14 of 80. So the first thing that I know is that regardless of which method I'm using, whether I'm using log or using ln, I know that 80 needs to go in my numerator and 14 needs to go in my denominator. So I'm just going to demonstrate both ways and kind of show you what our answer is. So I'm going to do log of 80, close my parenthesis, divided by the log of 14. And when I press enter, it tells me my answer is 1.660. And just to give us some context, what this means is that 14 to this power is equal to 80. So if you ever wanted to check that, okay, I could just go, okay, 14 to that previous answer, and notice it tells me 80. Now, if I put in a decimal value, it won't give me exactly 80 because that would be an approximation. But I just want to remind us what a logarithm is. A logarithm is an exponent. Now, let's say I wanted to do our natural logarithm instead. So if I did ln of 80 divided by ln of 14, amazingly, I get the same answer of 1.660. Now, I just want to quickly demo the most common mistake I see, and I know none of you guys will be making this, but I kind of mentioned the importance of using parentheses. So if I did log of 80 divided by log of 14 and didn't use any parentheses, what it's doing is taking the logarithm of this entire expression. So when I press enter, notice I get something that looks kind of reasonable, but it's definitely wrong. So I cannot stress enough how important it is to use parentheses. Okay, if we look at number 2, we have log base 6 of 14.8. So We don't have to use both methods all the time. We only need to use one, but I'm going to once again demonstrate using both just to show us it does not matter. On your homework, if it tells you just to solve, just use one method. That's great. So I knew since it was log base 6, my base has to stay on the bottom. Okay, and 14.8 is on the top. And my answer is 1.504. If you're not good at rounding, remember, if I'm rounding to 3 decimal places, if this number is 5 or higher, we round up. If it's less than 5, we just drop it off. Okay, if I had chosen to use ln because I am an individual and I like to do things that are slightly outside of the norm, guess what? We get the same exact answer. So we're not even going to do any more examples of this because I think you guys should probably have the hang of it. Our next 3 laws that we're going to be using today are going to help us know how to either expand or condense logarithms. And this becomes very helpful in our next lesson when we have to solve logarithms. This is a helpful tool to go ahead and use. So we're going to go ahead and look at these one by one. Our first property we call our product property, and we can see this is log base b of a times c. So these are being multiplied together. If I wanted to expand it into multiple logarithms, we would expand it using addition. Notice my bases are the same, so this would be log base b of a plus log base b of c. Likewise, if I wanted to condense it into a single logarithm, addition would turn into multiplication. Our next one is our quotient property. And so when I am dividing 2 terms, and I just want to point out that this is a single logarithm. It is log base b of a quantity that is being divided. The way we split up division is using subtraction. So product property is telling us multiplication goes to addition. The quotient property is telling us division goes to subtraction. And our third and final property is what we call the power property. So if I have log base b of something to a power, it's telling me that I can actually take this exponent and move it out in front to become the coefficient. And all 3 of these, I just want to stress, we can condense logarithms or expand logarithms using both of these. The way it's demonstrated here is more using the expansion property, but if we're condensing, that means addition becomes multiplication, subtraction becomes division, coefficients become exponents. So these are the 3 that we're going to be using. Our first set of directions says write as a sum or difference of logs. So basically, in order for us to do this, there's just some things we need to look for. The very first thing that I want to do is I want to expand by changing any multiplication or division into addition or subtraction. So that's the very first thing we look for. Then, after I've split it up, I want to look and see if there are any exponents that we can change into coefficients. So let's go ahead and look at number 3. Number 3 says log base 10 of 10x cubed y. So I'm going to go ahead and I notice that we have 3 things that are being multiplied, 10x cubed and y. So when I split this up, log base 10 of 10 plus log base 10 of x cubed plus log base 10 of y. Now I want to point out first of all that in this particular case, if you neglected to write the 10 here, you would be okay because we know the common logarithm or log indicates that it has a base of 10. If the base is anything else and you don't write something down here, that would not be good. You will miss some points for that. Okay, so we've done step 1. Now I'm going to look at these each separately and see if there's anything more we can do. So looking at this first one, log base 10 of 10, this actually kind of looks to me like what we did in a previous lesson. And we learned if these values are the same, it becomes 1. And if we think about it, it's because log of 10 divided by log of 10 is 1. Or 10 to the first power is 10 because we know a logarithm is simply an exponent. Our next one, log base 10 of x cubed, I have this cubed, so I'm going to move that out in front, and this is going to become 3 log base 10 of x plus, there's nothing I can do on that last one. So my final answer here is 1 plus 3 log base 10 of x plus plus log base 10 of y. So honestly, a lot of these problems are repetition. The more we practice it, the better we get. Okay, looking at number 4, the thing that I want to remind us of here is in terms of this radical. We know that the square root of x is x to the 1/2 power. And just to kind of remind us where this comes from, this 1 is the exponent that is attached to this value. The 2 is whatever our index number is. So if I look at number 4, this is a little bit different than the previous problem because this entire quantity is being taken to the 1/2 power. So the very first thing I'm going to do is rewrite this as log base 6 of the quantity 3x squared y to the 1/2 power over z, which would become log base 6 of 3 to the 1/2 power x y to the 1/2 power over z. I also want to point out when I'm writing this, notice this z is not dividing everything. It is always log base of this expression. So at this point, we need to split some stuff up. I see some addition and I see some multiplication and I see some division. So I'm going to group my numerator together and say log base 6 of 3 to the 1/2 plus log base 6 of x plus log base 6 of y to the 1/2. The reason why I used addition here is because this was all multiplied together. Now that we have division, I'm going to put a minus sign and then go ahead and say log base 6 of z. I want to point out that I put parentheses around the numerator and around the denominator. And the reason why that could become important is because of this minus sign. Sometimes we will need to distribute that, and that's a common mistake I see. So it's a good idea to always use parentheses and then adjust if we don't really need them. So now I'm going to go ahead and look at this. So log base 6 of 3 to the 1/2 power. I can move that exponent out in front to be the coefficient. So I get 1/2 log base 6 of 3 plus log base 6 of x plus, I can move that 1/2 out in front, 1/2 log base 6 of y minus log base 6 of z. Some of you guys in Algebra 2 last year, if you were in honors, did more complicated things with this. Today, honestly, this is as tough as it's going to get. So if I memorize those properties, you're in good shape. The second thing that we do with this, it says write the expression as the logarithm of a single quantity. So let's go ahead and just kind of outline what we're trying to do here. So when we are condensing, the first thing I'm doing is changing any coefficient into an exponent. Then I'm going to look and see if we have any addition or subtraction and turn it into multiplication or division. And the thing that I want to stress here is that our answer should be a single logarithm. So it should be log base something and then whatever's happening from there. So let's go ahead and look at number 5. Okay, the first thing I notice on number 5 is that we definitely have some exponents. So I'm going to start by changing, and by exponents, I mean that they're coefficients and we're changing them into exponents. There we go. So I have log of x squared. Notice we don't have a base here. That means that it is our common logarithm, so it's a 10. So I have log of x squared plus log of x plus 1 cubed. So I did step 1 and I changed these coefficients into exponents. Next, I need to still condense this into a single logarithm. I know I'm not done because I can clearly see I have 2 separate logarithms here. So since it's addition, we know addition goes with multiplication. So I have log of x squared times the quantity x plus 1 cubed. And quite honestly, at this point, I don't really care if we do anything more with that. And our final one of the day here, number 6, just to show us these properties apply to natural logarithms as well. I'm going to start by changing that coefficient of 2 into our exponent. Notice ln of x really has nothing, so I'm just going to leave it. Now, I need to change this subtraction into division. Now, I want to keep in mind the reason why on 5 and 6 we could condense is because both of these logarithms have the same base. So here I have ln of x plus 2 squared divided by x because we know subtraction leads to division. I think that's the easiest way to think about it, but let's say you think outside the box and you thought from this point, oh, that negative or that subtraction is like a -1. Okay, we know a negative exponent is like 1 over that x. And then if I multiplied those together because it was addition, amazingly, I get the same exact answer. So the whole point is there are a few different ways we could think about using these properties. I definitely think this first way is the easiest, but I just wanted to demonstrate that the properties hold true, or even explain why subtraction is division, is because of this concept right here. So that is it. Memorize those formulas and properties. If we don't memorize the properties, they're really difficult to use. And our actual examples will not be tough. The biggest thing I stress to you guys is memorize the properties.